recording going. All right. Let's just, I gotta exit out of this full screen mode. Okay. So yeah, welcome everyone. First official meeting, like I said. And yeah, this will be an introduction to Airplane, an essential primer. Very essential, very prime. Next slide. So, as we all know, Airplane is a movie released in the 1980s involving the wacky antics of a former pilot trying to win back his girl. Great movie, by the way. Recommend you all see it. Fantastic. A joke every 5 seconds. Good jokes too. Next slide. So, the legal definition of an airplane, according to the FAA, the regulatory body of the that regulates the aviation in the United States, at least. Sorry, I just had a message pop up. So, an airplane is a engine-driven, fixed-wing aircraft heavier than air that is supported in flight by the dynamic reaction of the air against its wings. Fairly simple definition. But if we go to the next slide, I want you all to let me know which of these is in fact an airplane. We will not be advancing until I get some answers.
I think the bottom left will count as an airplane.
You are correct.
Okay,
It has an engine. It is flown by the dynamic reaction of air against its wings. Although that one might, yeah, it is an IFE, but it is also an airplane because it has wings and an engine. It might require a little more hopes and dreams to fly than a normal aircraft, but you know, it is what it is. All right, any more guesses?
I really like the leftmost one.
Yeah. The top left or the bottom left?
The top left, but I don't know if that counts. Oh, it doesn't have wing. Does it have wings?
It has short,
Does
stubby wings, but it sadly, I think it's more helicopter than airplane. I wish.
Still badass
I wish.
though.
Very badass. Any other guesses? I know this kind of topic is difficult to handle at these late hours, but I'm sure I can get some more guesses about what is an airplane.
Which one is the bottom left one? Like what is it called?
That is called the Aerogavin, and it is not a real plane. It is not real. It's only art. Very sad. Yeah, top middle, fairly solid airplane, fairly big one too.
Bottom right.
C5 Galaxy.
Yeah, that's a C5. Bottom right is an airplane, of course. That is our airplane, the 2019 competition plane. Any guesses for the bottom middle? If you are afraid of speaking, you can always thumbs up or down in the chat. I've never seen a teacher actually use that feature before, but you are welcome to use it if you want.
Looks like a helicopter to me.
Good eyes. That is, in fact, a helicopter. What about the top right? That
very top right?
Yeah, very top right.
That's a glider.
Yeah.
It's a sneaky aircraft. In fact, that little black stripe you see on the top is an engine that pops out. But in this configuration, it is a glider. What about that middle right? Does that look like an airplane to you?
It's a nice blimp, or I forgot the other word for them.
It's a dirigible.
Yes, it does look like a bad idea. And will you reveal the answers, please, my dear co-host? Yep. All right, simple enough, all right? But let's get ready for the challenge round. Next slide. Which of these is an airplane in its current configuration?
Can you repeat the question?
Which of these is an airplane in its current configuration by the FAA definition? Let's start from the top left and go clockwise. Do you think that is an airplane?
I think that's
Yes.
an airplane.
Okay. Okay. How about the top middle?
I am confused by the top middle.
That's why it's the bonus
I
round.
don't think it's an airplane.
Don't think it's an airplane. All right. What about the top right? Is that an airplane?
It's
I'm
one
gonna
of
go
those
no.
military ones, right? The
Yeah. Yeah.
Osprey, is
But
it called?
does it have wings?
It is an
It,
Osprey.
it goes like that, and then it turns into a plane.
Yeah, but in its current
Mm.
configuration, is that an airplane? Top right.
No.
No,
Nope, it's helicopter.
I like that.
Or a
Okay.
UAV,
Osprey.
not UAV, it's a VTOL, I think it's called.
Yep. Detail. All right. What about the bottom right?
It is an
Is that
airplane.
also a vertical takeoff jet? No, it can't, is it?
That is the same aircraft as the top right, but in a different configuration.
Huh. Oh, I was
That's
looking
pretty
at
cool.
bottom left. Oops. Yeah,
Yeah.
bottom right, yeah. Yeah.
Left, right. All right. How about the bottom middle? Is that an airplane?
No.
Okay. Okay. Good assumptions. I'm not going to say if they're right or not, at least right now. How about the bottom left? Is that an airplane?
Yes. Yeah.
All right.
Yes.
My dear Jack, will you reveal the answers?
Yeah, I was gonna say that bottom left one's a little tricky. It's floating upwards, isn't it?
Yep.
Is that what it's doing?
Oh,
So-
what I forgot. What is it called? Is a shoot.
F-35B Lightning II.
Yeah.
What's the middle bottom airplane?
So, yeah, that's a trick question for you. Let's start with the top left. The FAA actually has no definition for what that is. It is technically a ground effect vehicle, also known as an Arcanoplane. And basically, for those of you who have taken more advanced aero classes, it uses the ground effect to create a cushion of air underneath the aircraft. But the FAA doesn't have an official ruling on what constitutes a ground effect vehicle and whether or not they are in fact aircraft. No one's really asked. So,
But if it's in the air at the time, isn't it an airplane if it's not touching the ground or water at all?
is it really
It's
flying,
just
or is it just kind of like?
a very low flying, limited altitude airplane.
But is a hovercraft an airplane then?
It doesn't have wings, and a hovercraft
Mm.
doesn't have wings.
Right.
Yeah, that thing's got dynamic reaction against its wings.
Well, the FAA doesn't know. Maybe give them a call.
I think that was developed by the Soviet Union
Yep.
in the times of the World War.
Soviet
Yeah.
Union. So the top middle is a hydrofoil, which has wings. It has engines, and it uses the dynamic forces against its wings to rise off of the surface. But it is a watercraft and not an aircraft. That one also actually has wings providing lift to keep it up on top of the water, which is kind of neat. Top right, of course, as some people noticed, is in fact a helicopter in that configuration, where on the bottom right, it's pivoted its engines down into the vertical position and is using the lift generated by its wings to stay in flight. The bottom middle is called a hybrid airship. And in fact, the airship cannot actually rise off of the ground. It is not positively buoyant. Instead, it is very slightly unbuoyant. So without forward motion, it starts to sink in the air. So it requires forward motion against the air to provide the dynamic forces to lift it off the ground. And it, of course, has engines. Basically, think about it as the three-lobed shape that serves as the gas bag is also a giant wing. A very giant, inefficient wing, but a wing nonetheless. And the bottom left is an airplane normally, but in this current configuration, it is hovering with the force of a lift fan and a jet turbine. So not an airplane in the current configuration. So yeah, it gets pretty complex. Evan, you want to talk about this? Well,
Me, Evan, or
yeah.
oh, all right, cool. I mean, you made these first few slides, so
Yeah. But
um,
you will be covering it in the next few, but yeah.
yeah, okay, cool. So now that I've got the floor, we're gonna talk about the actual like forces on the aircraft. Since Daniel's been talking about how we're getting these aircraft off the ground with wings, and that's a very important. Like the quote there is the dynamic reaction against the wings, and we're gonna basically go into the 4 forces of flight, which are real simple here. If you go, I don't know what this slide is. It's kind of just an introduction to all the jargon you're going to get. But if you go to the next slide, these aircraft are not just magic. There's actual real science that goes into how these airplanes fly. Except for whoever drew this little design here. So if you go to the next slide, you can see these are the true 4 forces of flight. Anyone who's ever tried to fly an aircraft or work for a company that flies aircrafts, the only thing that keeps you above is your dreams, and keeps you going is money. And if you don't know what the FAA is, you will learn very quickly that it is the Federal Aviation Administration, and they put all the rules just to bring you down. So this is how an airplane flies. If you want to go on to the next one. Oh,
Sometimes
actually,
the forces are flipped, and money is actually providing the upwards force instead of dreams, and dreams is pushing you forward. So
all right, so here's the part that I was actually prepared to present, is the actual aerodynamics design. And later in this semester, as part of our meetings, since we can't actually meet and build right now, we're going to be doing lectures, and I'll do a more in-depth one on aerodynamics. But here's the 4 basic forces of flight and kind of how they come about. You can see them there. They're lift, drag, thrust, and weight. So thrust opposes drag, and lift opposes weight. And then steady flight. So the airplane it's moving along, but it's not accelerating in any direction. It's not going up or down. Your lift is equal to your weight, and your thrust is equal to your drag. Go on to the next slide. First force that you see is lift. So if you put an airfoil in free stream flow, the flow going around the airfoil actually creates pressures on both surfaces. And the first equation that we're ever going to give you, and one of the few that we will, is that force is pressure times an area. So there's forces on both the top and the bottom of the wing, and if there's an uneven force, it pushes the wing in that direction. And lift is simply just the vertical component of that lift. So however much of that, or simply the vertical component of that force. So if that force is pushing you up into the sky, that is lift. If it usually comes from your wings, but you can see different types of lifting surfaces. So it's kind of the idea of airfoils as well, is to manage the flow over the wings. You can see in the top left, the wing is actually changing air angle, and it's changing the flow around the wing, which is actually changing the lift on the wing. If you go to the next slide, so as you increase the pitch of the wing, airflow has to flow faster over the top and slow over the bottom, which gives you more pressure on the bottom and less pressure on the top. However, sometimes you can do that too much, and you get to the top of that line there that the mouse is highlighting there, you basically just stop flying. You run out of creating lift, and your wing stops making lift, and you start kind of falling, and that's never good. We never want our aircraft to fall out of the sky. This occurs at high angle of attacks, which I guess we haven't defined for you. For those who don't know, angle of attack is basically how much the wing is pointing up at an angle. You can see that little angle drawn on the top diagram there. yeah, when that gets too much, the airflow that's going over the wing actually is no longer going over the wing, and it creates no pressures or low pressures on bad parts of the wing, and the wing stops flying, and that's not good. And there's a lot of different things that can cause this to happen, but the easiest one to talk about is just a high angle of attack. Go to the next slide. And the same force that's creating lift actually also creates drag. So if that force is not going perfectly straight up, it's going in the wrong direction, and it's pulling your aircraft backwards. There's other things that can contribute to drag, like skin friction drag. So that's just the actual air pushing against the skin and pulling your airplane back. You can kind of feel it if you stick your arm out the car window. You can kind of feel your arm being pulled back a little bit, especially if you put your hand forward. There's a lot of force on your hand that's pulling you back. That's drag. That's yeah, I don't know what else to say about drag. It's there. You go to the next slide. And then thrust. So this is, now we're getting into a fun force. Thrust is used to oppose drag. It's where all your engines come in, and you like to, well, so if you can't overcome drag, you can't take the airplane off the ground. But if you keep going with thrust, you can overcome your drag. And then at cruising, you actually want your thrust to equal your drag, because those are forces. So if you have equal forces, you can continue at the same velocity without accelerating. Yeah, okay, next one. And finally, the weight of the aircraft. It's real simple. You put the airplane on a scale, and that's how much it weighs. Sometimes you can fit an airplane in a scale, sometimes you can't. We can put ours on a scale sometimes.
Sometimes we need some help.
Sometimes we do some modifications to our scale. Sometimes we have our mass properties lead do some fun stuff with our airplane. But it's really just weight as you think of it. If you want to get technical, it's still the mass times the acceleration of gravity. So weight is still a force. It's still a mass times an acceleration. And that line there at the bottom is kind of one of the most important topics in aircraft design. Is the heavier your aircraft is, the more lift you need to do to oppose that weight. But the more lift you have, the more drag you're going to get, because remember, that force is going to be greater. And to overcome that drag, you're going to need more thrust. But to get that thrust, you need bigger engines, which is going to give you more weight. And when you have more weight, you're going to need some more lift. And you guys kind of get the idea. It's just going to keep going in circles until you find something that works. And it's not just a straightforward process of here's an airplane, make it fly. That should be all I have on the 4 forces of flight. So whoever's next can take over airplane parts.
Yeah. So basic airplane parts. Here are some of the ones that we use here in Air Devils. You're going to see this on every aircraft in the air. Of course, you got to have your canoptic jars, the vestigial head, intakes, neck, and antenna. So, you know, you're going to see this on every aircraft in the sky, but now you know how to describe it. Especially the love handles. Can't forget those. Next slide. Here are the actual airplane parts. There's a lot of them. Some of them have different names. Horizontal stabilizer, vertical stabilizer, rudder, elevator, flaps, aileron, spoilers, slats, fuselage, cockpit, the engines, of course, and one of the most important things on the aircraft, the wing. You need all of these pretty much to fly, though sometimes it'll be in a different configuration than what you see in the sky. And below each of these different airplane parts is one of the basic functions of that. Sometimes you'll have aircraft that don't necessarily have a conventional horizontal stabilizer, vertical stabilizer, and rudder. Instead, they will have just one giant wing, and those parts will have to be sort of built into that wing. But this is a basic configuration and the basic names and what they do. Really simple. Next slide. We'll talk a lot about things to worry about when the aircraft is moving dynamically, so when it's not flying straight and level. As said on the previous slide, elevators, which are on the back of the aircraft, cause the aircraft to pitch up, pitch down, basically rotating around its lateral axis through the wings. It pitches. The ailerons that are on the ends of the wings will cause the aircraft to roll, which is, if you're flying straight, this is roll. And finally, yaw, which is, moving along the vertical axis, as the diagram pretty easily shows. So those are the basic movement terms that we'll use, besides going forward and going backwards. Hopefully not going backwards. Next slide. Everyone has a different idea of what an airplane should look like. And if you look at that little comic there, you'll see that each of the different groups has what their ideal aircraft will look like. As someone who has been part of a production engineering group, that is definitely what the ideal airplane looks like to them. A block of wood nailed together. Definitely the ideal aircraft. But it's basically a series of design studies, compromising assumptions, propelled with enough force, and is designed such that it requires minimal lifting gas and the occasional singularity to allow the numbers to line up, and for the platform to leave its earthly shackles. An airplane impresses on the world your mastery of the sky and showing those stupid birds who's boss. It's all about showing the birds up. Next slide. And here's just an introduction to what we're dealing with. On the first day, there's gravity, and the spirit of Newton said that formula, and matter became weighty, and so on and so forth. The devil created drag, of course, and there's a lot of different things to take into account. But of course, he who controls the purse strings controls the policy, and then there was economic reality. Damn Keynes, Keynesian economics. You really screwed the pooch for us aircraft people. We have to take into account economic reality when designing things. Next slide. So, of course, what you were all here for, terminology. What is an aircraft? Or what are all the parts that we're talking about when we say ESC or receiver and everything? Well, if you go to the next slide, someone will tell you. Oh, is Atish not here? Evan, do you want to describe what some of these aircraft parts are? Evan D.
Oh yeah, I'm here.
All right.
All right, yeah, let's look at this thing. All right, well, they're all labeled, so we know the names. So I guess we can start with the LiPo. So a LiPo is a battery. It's a lithium polymer battery. They are the new age battery, I guess you could say. They're highly dense in energy compared to weight and size. And so a couple things about the LiPo, I guess. Well, we'll get into it more, right? So I don't really need to talk too much.
Oh, hey,
But
just in time. Tish is here.
just are we talking about everything or just a little bit right now?
Just a little bit, like the ESC and receiver especially.
Okay, yeah, well, the LiPo, so you can judge how much energy they have in watt hours, and there's some equations for that with the size of the cells and the voltage and whatnot, and they're kind of categorized in cells. So a 1-cell battery has one little LiPo pack, and a 3-cell would have 3 that are connected in parallel, I believe. No, series. They're connected in series, so the voltage goes up. And so a LiPo, each cell is like 4.2 volts fully charged. And so when we use like a 6-cell battery, we're at 25 volts. So we get up there in power. And then the LiPo plugs into the ESC, and the ESC is kind of the power distribution for everything. So it goes to the motor with 3 wires, and the 3 wires I think are called like phase wires. So they control the motor and which magnets to power up to make the motor spin. And So I guess, yeah, it goes to the motor. And so these are brushless motors. So there's two kinds of motors, brushless and brushed. Brushless are the new school motors, all fancy. The old motors were brushed motors, and they actually had little, I don't know what they're made of, but little, they're like carbon type pads that actually contacted the inner surface of the motors, and they would eventually wear out after a long use. So you'd actually have to replace the motor parts after a while. And the new brushless motors don't have any of that. They really only have one spinning part, and they're really simple and powerful. So then if we go back to the ESC, it has another the little tiny wire is, those are kind of servo wires. And so that wire in particular it has 3 wires in that little single, well, it's a triple wire all connected. So there's a power, ground, and a signal wire. And the ESC provides power to the receiver, and then the receiver sends that power to the servos. So we go to the receiver, and the receiver is what talks to the radio or the transmitter, and that takes all your signals and turns it into actual movements. And so then that will go back through all the signal wires, and tells each servo or the ESC what to output. And the servos are just little, what would you call that? Just a little control mechanism. It's a little motor with a little arm, and it moves back and forth a certain amount compared, or with your radio movements. So that's how you get all your ailerons and moving surfaces to go. And I think that's about it here. And then let's see. Yep, the brushless motors. So you have the 3 wires, and then there's magnets on the inner part of so there's the whole outside of the motor you see actually spins with the shaft, and the only thing that stays put is the very back part, and that connects to your motor mount. And then there's the inner part, which is called the stator, and that's where all the electricity flows. And there's windings in the motor, and that goes in a certain pattern to pull the magnets, which are on the inside of the outer portion, which is called the motor bell. So the inside of the motor bell has little magnets, and you send current through the stator in the correct way with the 3 wires, and it will pull the motor in a circle. So that's how you get the spinning torque. And then you see there's a whole lot of different propellers, and you kind of have to choose your proper propeller to the motor and the application you want. So you can kind of get into really detailed things, like you get there's a couple ways to measure a propeller. There's diameter and then pitch. So the pitch is how twisted the propeller is. And in short, the more the pitch, the faster the airspeed. And then the more the diameter, the more kind of static thrust you get. So you got to balance both out to your application. You could either have a low airspeed propeller with a lot of pull, or a high airspeed propeller with less pull, and they both have like the same power rating. So that's a really big field and kind of technical to get into, but I think actually on our Slack, we have a couple little resources you could look into, and it kind of will give you some propeller and motor specs. So that's kind of cool. And that's about it there.
Can you exit out of the slide real quick, Jack, and go back in? Yeah.
Oh, there's a new one.
Yeah.
Yeah, so that new one there is called a EDF, an electric ducted fan. So it's pretty much just a little kind of jet engine. It's a ducted fan, so the outside makes the propeller more efficient because it stops the what's that called, the the tip vortices or whatever, right?
Yep.
Yeah. So that's another thing they get into. But in short, those are made for really fast and high power applications, but they don't really give you a lot of low end thrust, which is what we usually need in the club. So they're really cool and they have their specific design applications, but you probably won't really see much what we're doing.
I wonder if, since we don't have a takeoff requirement or a 100-foot takeoff requirement this year, we could probably get away with the EDFs.
It would be fun. It would definitely be sick.
Yeah.
They
Something to think
just
about.
are, they suck up crazy amounts of power,
Very true.
but they're cool.
All right. Next slide.
All right, now it's my turn. Okay, I'm gonna talk a little about structures, both like RC, like how we're currently building our planes, and a little bit about how commercial airplanes are built. And so we're gonna start off. I'm just have a bunch of pictures, so I use the pointer a lot. So here is the pretty much bare essentials of our plane that we built for the 2020. It's our wing, our tail, and they're all attached to this carbon fiber keel. And then the three essentials: carbon fiber, a very modest amount of CA, and a bunch of different types of wood. And that culminates in our plane, as you can see here. And we also do quite a bit of testing for our structures, but not always. But like we now have a MATLAB code that allows us to develop optimal. Oh, we'll get to it. Okay, so the wing consists of a pretty much a torque box right here. It's, as you saw in the previous one, this big old box, and this carries pretty much all the forces on the wing. And then it needs these ribs to prevent buckling, and it also strengthens, and it also provides the form for the wing. And so that's when we build our wings. It's pretty much torque box, ribs, and then we cover it in monocoat, which is a plastic material. It doesn't take any loads. It's just there to provide the structure for the air for it to go around. Now here is a segment of an actual wing. Well, picture of it, but it pretty much contains the same thing: ribs that go along with the how the air would move. A front, two spars, a front spar, rear spar. You can see we have the same sort of thing going on here. And the big difference is they always use stringers and a skin combination, which provides a lot more strength. We don't do this at all because it is incredibly difficult to build, because that would be a lot of tiny parts for us, and we could just easily get by with just a thicker piece of balsa. But that's how all the planes have, and you'll see these this skin stringer combination everywhere in the plane. So and here's a couple pictures of other parts of the plane. I took this out of a structures book that's just for aircraft structures. No need to go over it, but that's kind of the I'll be posting later in the Slack under the resources the book, so you can take a look at it. Okay, so there's pretty much two big ways to design a plane. They're all built monocoque right now, like nowadays, but I mean semi-monocoque. Monocoque is the skin holds pretty much all of the forces, and you have occasional formers and bulkheads, which help keep the structure from crumpling on itself or whatnot. But this is pretty much like an eggshell, so that's how they're designed. It is not the most efficient way because does not deal with buckling very well, and there's also, well, it doesn't deal with certain forces very well, and so all modern planes use a semi-monocoque structure. So it has the stringers, it has the skin, and then it has a bunch of other stuff layered on top, well, layered underneath. So here is a picture of the fuselage, which has all this stuff built inside of it. And of course, there's also some additional tracks for where the people would sit. And the big difference for us is that we are not doing this kind of structure on the outside. We use a single carbon fiber keel that carries the structure, and it's a lot easier for us to do the math behind it and do the ANSYS or whatever we need to do, figure out is it going to break or not on a single piece instead of having all these tiny stringers or whatnot. And of course, it is significantly easier to build. And you can kind of see we have formers in there as well, although this is not for structural reasons really, just to keep the shape of the body. Because right here, this big old box, this is where our cargo or passengers for the 2020 mission would sit, and that they're resting right on the keel. And the wing also goes right under on the keel. Landing gears on the keel, tail, all that. Those are drilled in and glued on the keel. All right, and a little bit more on this kind of applies to both the wings and the tail, is that they're built with all this madness. I don't know how anyone gets these things built, but it's a lot of stringers. They throw in honeycombs, skins, whatnot. For us, we tend to do a lot simpler. So we have a front spar, a rear spar, and whatever this would be. So pretty much it's just ribs and spars, and then whatever is needed to keep the form. This back plate also really helps with twisting. And those are drilled directly into the keel and glued. It's quite sturdy, and you can see here there's no holes for wires. That was a mistake that was a pain to correct. And this is the vertical tail, and this is its rudder. And so you can kind of see how this would attach there. And then this whole vertical tail goes on the box along with the horizontal tail. And so that's pretty much our carbon fiber keel right here segment. You can't see, but they do a similar thing. And the most entertaining part about our aircraft is the landing gear. It's just a piece of carbon fiber. So, they're the same thing. T is actually releasing a book pretty soon on landing and takeoff performance. And just the other day, I was walking with him, and he told me about how the aircraft is completely sized just on the landing gear. So he knows quite a bit, or is quite fond of landing gear. So if you want to know more, you can talk to him. One quick thing on positioning, I noticed this actually came up, is that whatever the highest angle of attack you're planning on taking off, you're going to want to place your landing gear accordingly, or change your rear of your aircraft so you don't tail strike. And as far as the structure of landing gear, is pretty much a strut to absorb your landing or crashing, depending, and a T to hold the wheels. And right here is our front landing gear, which is just this coil helps absorb, and a wheel attached to a hinge, and you can see a servo arm right here that turns it left and right. All right, and whoever's next.
Yeah, so here are some of the basic materials that we build with here at Air Devils. Are basically three basic parts: balsa, carbon fiber, and plastic. They each have their advantages and disadvantages. Balsa, of course, is lightweight. It's a composite, so it sounds cool. It's relatively cheap, not as cheap as you'd expect, and it's easy to work with. Whether or not it's an advantage or not depends on the application, but balsa is very bendy. It's not very stiff. Disadvantages of balsa wood are that it's soft, it's susceptible susceptible to water damage, and it's anisotropic. Never had to say that word aloud before, but basically,
What does that mean?
it
Oh, you're
means
gonna
that
say
it
it, okay.
doesn't have the same strength in every direction. And basically, a piece of balsa wood has distinct grains in it, and it is very likely to split along those grains if you fold it parallel to those grains. But if you fold it perpendicular, it is very strong relatively. Another advantage of balsa wood, of course, is that it smells good.
I would like to say there, Daniel, I think it's only a composite when you start gluing it together.
It's technically a composite. It has cellulose as the fiber of a composite, and
Okay.
the materials in between is called lignin, which is sort of
Oh,
like
so it's
the
actually
glue.
like different? Okay.
Yeah,
I
technically
didn't
a
know that.
composite. Another type
Heck
of
yeah.
composite that we use is carbon fiber. Carbon fiber, of course, is very strong, very stiff, but it's also very expensive. Also anisotropic, but we don't worry about that as much in our applications. We don't really have to worry about the strength because we're usually using it as a lateral member, like for example, the keel. And so it's only ever going to be bending in one direction. But also, for example, on last year's plane, we decided to go with a square keel, as you can see in that picture in the bottom right. And that is very strong, very stiff, very resistant to bending, but it's not very resistant to twisting. And so on our 2020 aircraft, we are having cracking occur. Is it on which side of the joint is the cracking occurring, Evan?
It's the two bottom corners. I think it's more like compression, like
Okay.
when the landing forces push up on it instead of
Twist.
kind of throughout the whole thing is what I'm thinking.
Okay. But yeah, it has its own technicalities to it, much like balsa wood. It's also difficult to work with because it's so expensive. We usually buy it in preformed pieces. We can do layups. We have the equipment to do that kind of thing, but it's very time consuming and labor intensive compared to balsa wood and plastic, which of course, plastic is our third material I'm going to talk about. It's stiff but brittle. It's cheap, easy to work with. Depending on what kind of plastic we're talking about, it could be isotropic. Over 3D printed pieces have their own issues with layer adhesion, so they're stronger if you're going with the layer than in terms of pulling them apart. Smooth, plastic's very smooth, so that's most of the exterior of our aircraft is plastic because surface roughness does actually play a part in how much drag our aircraft has. So very smooth structures are very good. And it can also be fairly heavy for an equivalent structure. That piece that we have in the center there is the what holds together the two distinct parts of our aircraft. We basically have a wing that is made almost entirely of balsa. Then we have the keel, which is carbon fiber, and we use a plastic piece to clamp the two together. But that piece is pretty heavy, honestly, for what it does. But it needs to be very strong because it's keeping the aircraft together. It is the it is the glue of the plane, besides the actual glue.
One thing I would like to add is the balsa is quite useful because you can make it thick without gaining a lot of weight, which helps with the buckling of the aircraft. You'll learn in your structures class that buckling is dependent on the geometry of the part or whatever. And so even if we were to do like a thin sheet of steel, that would help like some parts of the structure, but it would still then we would have be sizing on buckling, and then we would have to add a whole bunch more thickness. But with balsa, it is already so thick that it really helps. So
Yeah, I don't know how well this
that
shows up, but like that's a buckling force, and we don't want that to happen on our aircraft because then it crumples quite violently.
yeah, and our small aircrafts are really dominated by buckling, opposed to it ripping apart as if you were just to tear the paper.
Yeah.
So, anyways, I'll
like that. It's not going to rip apart. It's going to
All
buckle.
right,
and
but
then...
that rip is more of a shear, I think, instead of a actual pull apart. What is that pull apart called?
I don't know. I should know.
Tension. Torsion.
Yeah, right. Yeah, not torsion. No, what is it? Compression and well, yeah, we'll sell there.
I think it is shear, but yeah, shear is in all sorts of
Shear
different
is this.
directions. Well, it shear is in it's in every direction pretty much.
I think it
It's got
fails in tension. That's what
transverse.
we're talking about. I don't know.
Failure
Yeah.
intention. Yeah.
Structures are hard.
Yeah, you'll take it and then you'll regret taking it.
All right. Is Max here?
Oh yeah, okay. So these are some of the more basic and common control systems for aircraft. Starting on the left, we have what's mostly seen in like smaller, possibly a lot of general aviation aircraft or aircraft back in the day, where you have cables and pulleys, and you had to use your big old muscles to yank that stick back if you were, diving. And then your control system, controlling those actuators was you and your brain. You didn't have a computer running those and making sure you're stable. So it was kind of all up to you. Flash forward to today in the more advanced stuff on the top right. This is the type of stuff you'd see in more high performance aircraft or in larger aircraft where you're using electronics and hydraulics to actuate your control surfaces, like your aileron and your rudder and all that good stuff. Right under that, you can see like that's a servo motor, a linear servo motor. So it'll extend out and then cause rotation of a control surface. And under all those pictures, the lower right, you can see the types of servos that we use for our controls. They're small, they get the job done. Our servos don't need to be very powerful to do what they do, but they do need to be powerful enough because there are very weak servos. There's a whole range of different types of servos and strengths, and that's a whole little art to it as well. But those types of control systems go to a controller. And the analog for that, for what we use, is the receiver transmitter, I guess, as opposed to a, I should say maybe real world controller that does in-flight
Like a flight
communications.
control computer or something, yeah.
Yeah, that like ensures stability and maybe does some sort of autopilot stuff. We don't really use that, but we do use receivers and transmitters.
Like a stick shaker that's supposed to prevent you from stalling the aircraft, but instead forces you to nose first into the ground on a 787 or 737 MAX.
Something like that, yeah. Something called MCAS.
No MCAS. Yeah. Next slide. So one of the things we'll talk about a lot is wing dimensions. Here's a good slide from NASA, like I've stolen a lot of other slides from, that gives an overview of what do each of the, what do we mean when we say chord, span, centerline, camber, all that sort of stuff. It's only really important for the arrow what each of those impacts are, but it is good to know that when we're talking about along the chord line of the aircraft, we're talking about it moving back and forth in line with the fuselage, whereas if we're talking about span, it's going horizontally across the span. And yeah, different aeronautical terms. The wing can, of course, take a whole bunch of shapes. Go to the next slide. A whole bunch of shapes. We mostly use a simple rectangular wing with maybe a slight taper to it because we, of course, are not bound by compressible flow, and so there's no real reason to have sweep on our wings unless we want to try and move our structure away from our center of gravity, but we don't really have those issues. If you go to the next slide. Bunch of other things we like to talk about is what is the plan form of the wing and where is the wing located on the body. As you can see, there's a whole bunch of different options. Dihedral is when you have the wings at usually the bottom of the aircraft, but then have the wings up, and it basically lowers or raises your center of pressure for stability reasons, because an airplane is a dynamic object. But again, it's a little advanced. There's anhedral, all sorts of different stuff. We'll also often talk about delta wings, which are the bottom two of the wings on the right. Those have certain advantages. They're usually fairly efficient wings, but we don't really use them because they're also super draggy in a turn. They don't really keep the energy of the aircraft very well. So they can be dangerous and easy to stall. Go to the next slide. And yeah, other people have brought up the different control surfaces in our previous one. Or I have talked about them a little bit before, but here is a list of all the different control surfaces on a plane. We use basically none of them but rudder, elevator, and aileron. Sometimes we have considered putting flaps on our aircraft, but we never actually have. Trade-offs just aren't worth it. And yeah, last but not least, the tools.
I got this. Yeah. So tools. These are just the what were used to build the plane. Bandsaw. Well, you've probably seen most of these before. This is a bandsaw. You pretty much take a piece of wood, move it along, cuts it. 3D printer. We all know that. This is the closest thing I could find that looks like our foam cutter wire.
Yeah, that
It's
looks really good.
Yeah, it's a hot wire, and you take the foam, and then you usually have some wood on it, so it doesn't. You can pretty much conform the cut to the way you want it. Drill, soldering iron, files, CA, which as Daniel put in the chat is super glue. X-Acto knives, we use a lot of those, and a laser cutter, which ASU has a building for, and you can go use. I don't know about COVID, but I used to be able to use them pretty much anytime you wanted.
I think you have to schedule a time now to use them.
Oh, that sucks.
Yeah. Yeah, so those are the basic tools. I guess I should probably put this on the materials slide, but during the prototyping process, we also use a lot of foam when we're designing and building our aircraft. Foam is really easy and quick to build and to design and cut out. So we just laser cut some ribs that conform to the shape, and then we use those as guides for the hot wire. And then we just simply cut along those guides, and now we have a wing shape that we can then use to test. We don't usually use them on our competition planes because, believe it or not, for how light foam seems, that balsa wing, if you go back a few slides, bunch of slides, there, that balsa wing is really light for all the weight it can carry. If you see what our former president Nick in that top picture is doing, each of those bags weighs what, 2.5 to 3 pounds?
Yeah, I think they're 2 pounds each, and we did, what was that, like 10 on each side? I don't know.
Yeah.
Yeah,
It's
that
like
thing
10
was
on each
crazy.
side. And so balsa wood, while it might seem like a archaic, something archaic to be building an aircraft out of, and is in fact highly discouraged by the FAA to use any sort of wood, it works perfectly for what we need it to do, and it is very easy to work with compared to, say, metal or composites, or more advanced composites, I'll say.
Where is Nick now?
Nick is going to grad school at Georgia Tech. He's getting his master's.
Is he going to go into DVF for Georgia?
We better hope not. That'd actually be kind of cool to see him at competition.
Yeah, that would be sweet.
Yeah, we'll see. But yeah, Does anyone have any questions about anything RC related or aircraft related? Used up our time fairly efficiently here.
So a fun fact about balsa is all the best balsa is going to manufacturing the big wind turbine blades, and balsa is really only grown in like I think it's Malaysia. It's really only grown in one country, and China's taking all the best balsa to make wind turbine blades. So all the balsa we get is really kind of second grabs, and it would really be interesting to see what the best balsa actually looks like.
Get that high quality stuff.
Yeah.
And could you go back to the wings slide? Not this one, the other one. The one with anhedral and dihedral ones.
Okay.
Yes, that one. So in that, I wanted to know, like, what exactly does gull wing and inverted gull wing design do to an airplane? Like, and why, and what are the lift formations, like lift
Okay.
distributions on there?
Yeah. So basically, the distributions on those will be pretty much exactly the same as if it was a straight horizontal wing. Why do they have inverted gull wing and gull wing, dihedral, and anhedral? It really depends on what purpose the aircraft is for. If I pull up,
I don't think I've really
I
seen
was
a
able to
gull wing plane
understand.
before.
Sorry,
They-
I was able to understand the dihedral and anhedral ones, but the gull and inverted gull is like kind of like weird to me. I'm like, why?
Yeah, I don't think, Daniel, do you know a gull wing plane?
there were
Oh, there you go.
several. Yeah, look at that. So that's a gull wing.
It doesn't really have like anhedral on the outer portion, so it's kind of just like, well, I guess it's
Yeah.
still a gull wing though. I
Can
don't
you
know.
pull up an F4U Corsair, like Google Corsair head on?
We need to find a picture with the landing gear down too. Is
Yeah.
more specifically what we're going for.
Here's
Okay, that's fairly good. So, of course, as I mentioned earlier, aircraft are a series of design studies and compromises. So on this specific aircraft, it has an inverted gull wing for two reasons. One, there was a NACA report that showed that a mid-wing was the most efficient configuration to have on, like, it produced the least amount of drag compared to a low or a high wing. So they wanted to have a mid-wing, but doing so and having the landing gear on the wings would have meant they would have had extra long landing gear, which had to be extremely heavy in order to fit the giant propeller they have on the front of it. So the gull wing allows a compromise between,
Oh yeah, that's a good picture.
yeah, it allows a good compromise between allowing the landing gear to be short while also allowing the propeller, which is huge, like I think it's what, 14 feet diameter?
Yeah, 13, 14, yeah.
Yeah, absolutely massive. One of my favorite planes. But allows
Wow.
that propeller diameter to be larger than it would be, because otherwise it would start striking the ground. You don't want that on a plane. And the other thing that a gull wing allows you to do is if you close out those two, or just minimize them, I guess, it
Yeah,
allows
makes
you to
sense.
do some sort of dihedral as well. And the reason you want dihedral and anhedral is that it changes where your center of pressure is, which is basically, if you were to average out all of the lift on the aircraft, all the lift generated by the wing, where would that be? And it changes its vertical position relative to the center of gravity, which influences the stability characteristics of the aircraft. Having a dihedral wing allows you to have your center of pressure closer to the center of gravity, which gives you a higher roll rate which is important depending on what you want to do. And
Makes sense. Yeah.
anhydrol are super stable, extremely stable,
Uh-huh.
because it's acting like a pendulum in that the lift, basically you can imagine it as trying to see if I have anything that's pendulum-like around me.
And the only ones we have made were majorly like mid-wing, right?
So the 2019 aircraft is a high wing. The 2020 aircraft is a low wing. They have very, very slight dihedral, not even that significant.
I think it's more of the twist is what we see, because
Yeah,
the wing torque box is actually flat. Well, actually, I guess there is a very little bit. But
yeah. One
You're
side of the
right.
wing torque box is flat, and the other one is very slightly has a, I don't know how to
Angle,
describe
yeah,
it.
I
It
don't
has a
know.
slight angle to it.
Makes sense. Yeah.
Slope.
Yeah, it has a slight slope to it. So they are technically dihedral, not really. But yeah, the lift distribution is, if you go up a couple of slides, down one. Yeah, this kind of shows what I think this shows what the lift distribution is. I don't know.
I think that's the stall
Okay.
progression.
Yeah,
And this is for like the wing design. This is like the tapered
yeah.
and
This is
regular
like
ones.
the
Yeah.
plan form of the wing,
Yeah.
whereas the other slide is more the other characteristics of the wing.
Yeah. Makes sense.
This is its plan form. The other slide is the configuration.
Uh-huh.
So yeah,
Thank you.
no problem. But yeah, like I said, you can't always design a plane to have the perfect drag characteristics, the perfect coefficient, because sometimes, sadly, other things get in the way, like being able to take off and land. Other cool thing about the Corsair is that you can use its landing gear up to like 500 miles an hour or so, no, 400. You can have them out because they are built so strongly to be able to land on carriers that you can use them as air brakes to increase the amount of drag the aircraft has. On a normal aircraft, you do not want to have your landing gear out past maybe 150, 200 miles an hour because they can actually rip off.
That is a pretty good little fact there. A lot of people don't realize that, and I sometimes forget that. But yeah, having the landing gear pop out at like in a full dive is pretty sweet.
Mm-hmm. I guess that's something else we can talk about is that none of the aircraft that we build have folding landing gear.
True. That'd be cool, dude.
I'm not sure there's any pictures of it, but yeah, all of our landing gear is fixed. And that's mostly because there are significant drag reductions with having landing gear that fold back into the aircraft. However, at the scale that we have, those basically the drag is relative to their surface area. And those large landing gear on a regular aircraft are much larger relative to their surface area than the landing gear is on ours. Just different factors scale differently. And so on a small aircraft like ours that isn't going very fast, the landing gear produce less drag than what would be required to have them be folding and retract back into the aircraft would cause, because that folding mechanism adds weight, which means we need more lift, which means we need more drag. So again, that continual and perpetual and devilish loop of more weight to more drag to more lift.
Yeah, and the other thing for the scale we're doing, the small 5-foot wingspan planes or so, just building it is really hard enough. So going with the simplest structure and just getting it done is really the main priority. And yeah, it would be really cool to incorporate folding landing gear, but then you gotta find out how to attach that to the torque box and make sure the mounts are good. Then you gotta actually pick out the landing gear you want and make
Mhm.
sure that can take the loads you need. And especially with like model planes compared to full-size planes, you could have really easily an unpredictable landing. And for a model plane, taking a pretty big hit is not like out of the ordinary compared to a full-size plane. So you really kind of, for scale-wise, you need to be a lot stronger than like a full-size counterpart.
Yeah, you don't have someone in the cockpit who's able to feel how the aircraft is responding to the air around it. How it's, if it's experiencing stall, is a big thing. You can kind of see it, but it's, if you're in the aircraft, you can actually feel when the
Yeah.
aircraft starts to stall. And so a landing tends to be a lot harder on our scale of
Yeah,
aircraft.
when we go actual flight days, you could see high angle of attack and everything, and then there's issues like when you're coming right at yourself when you're flying, it's really hard to tell how fast you're going compared to flying by yourself. So that's when you could get into issues. But yeah, that compared to actually being inside the plane is a whole different story.
Did you have a slide? I'm sorry. Did you have a slide for the remote that we had?
Oh no, I don't think we do.
Oh, okay.
What's it
You should pull
called?
up a picture. It's a Spectrum
Yeah,
transmitter.
really just any one will do.
I think it's a DX8.
DX8, DX9, I don't know. I think DX9. The one we have now is a Tranix QX7, but
actually, do we have
any
DX6?
Yeah, that works. Yeah, we have one of those. Yeah, so that's the transmitter radio. So you have the two sticks, and those move up, down, left, right. And so on the left stick, I guess there's different modes, but for how we fly, the left stick, the forward and back is your throttle, and the left is right is your yaw with the rudder. And then on the right stick, left to right is your roll with the ailerons, and up and down is your elevator pitch. And then all the switches just control auxiliary channels. So for an RC plane, you really have four main channels, which is your throttle, pitch, yaw, and roll. That's it. So you got those four, and then whatever else you need to do. So like previous years, we had like bomb drops and banner dropping and whatnot. So that's what all the extra switches are for. And then the bottom portion there is a little screen, and you're able to do all the radio controls there. So it's a little computer, really. You could modify how things move and how things interact, and putting what channel to what switch. And they could get really complicated, but they're just like everything else. You specialize into it, and it's its own little thing. So
yeah,
we'll be doing that this year for sure, because we gotta figure out how to turn on and off our sensor and roll it up and down. So
we can actually have a second transmitter, so we might
yeah,
actually
that
do
will
that.
also help. Yeah.
Just as to give a demonstration, I have this just sitting below my desk, but this is a flight stick. You pull back on the stick to pitch up, down, go down. You can rotate this, but I don't think you can rotate the sticks on our transmitter.
No, there was a UAV drone quadcopter I was flying that actually you could rotate the sticks to yaw it, and it was really cool.
Yeah, on this there's little switches to do yaw. So.
Oh, okay. Yeah.
You just have that at your desk, Daniel?
It's for flight sims, but yeah.
Oh, okay, that's good. Which class?
It's not for a class. It's just for fun.
Okay.
I wish it was for a class.
Yeah, I don't think we have any classes, sadly, that do that.
Yeah, maybe in the private pilot program. Commercial flight, I think.
Yeah, probably not really. It's not really. It's all in a classroom. It's not actually doing it at your home, which is kind of sad. It'd be cool to have home training like that, though.
Maybe in the online college they'll have some virtual
Yeah.
flight sims.
Yeah, my roommate's in the professional flight program.
All right, I'm gonna go ahead and end the recording there. Seems to
Yeah, seems good.